reactions. Yesterday we learned a few rules about oxidation numbers. First of all, if it's an element, the oxidation number is what? 0. If it is an ion, monoatomic, it's equal to the what? Charge. If it is a compound, group 1, group 2 tend to be +1 or +2. And halogens, fluorine is always -1, and the halogens are usually -1 unless there is oxygen or fluorine in the compound. Oxygen is usually what? -2 unless it's in a peroxide. Hydrogen is usually +1. It can be -1 when it is with an alkali metal in a hydride. And then the one thing we know is that in any compound or ion, the sum of the oxidation numbers has to equal the charge. And that's how we determine oxidation numbers for other elements. So, balancing redox reactions, we use our oxidation number information and our oxidation reduction reactions, half reactions, to look at how to balance these redox reactions. Now, this picture here, does anyone know what this might be? Ooh, it might be a mitochondria. Let's look and see. Hopefully. If I can get this to move forward. So you've got your wonderful inner membrane and outer membrane and your proton gradient. You've got your oxygen turning into water and your NADH turning into NAD+. You got your wonderful biology. And if you haven't had biology, you're like, oh, that's pretty, what is that? I don't know. That's okay. Because oxidation reduction is a very important concept that we're going to look at today. In oxidation reduction, there are certain reactions which are called disproportionation reactions. I can barely even say the word. Whoa, why is it such a big word? This is when an element in one oxidation state is simultaneously oxidized and reduced at the same time, or at least as far as we can tell at the same time. This is an example of one of these reactions. Chlorine plus hydroxide ions. What happens here is you start out with 0 for the chlorine, -2 for the oxygen, hydrogen, +1. And here we've got +1, -2, -1, +1, and -2 for the oxygen. You'll notice the chlorine goes from 0 to +1 and to -1 at the same time. So this reaction, it looks like chlorine, what starts out as Cl2, 2 chlorines attached to one another. As one breaks apart, they break apart. One of the chlorines gets oxidized, and the other one gets reduced. In the oxidized one, it is gaining, it's losing electrons, it is increasing its oxidation state, and in the reduction, it is gaining electrons and going from a 0 to -1 oxidation state. So if we were to write reactions for this, we need to look at the reactants must have an element that can have at least 3 possible oxidation states. So in order for it to be a disproportionation reaction, the most common elements for disproportionation are tin, manganese, iron, copper, gold, mercury, nitrogen, oxygen, phosphorus, sulfur, chlorine, bromine, and iodine. You'll see some of these are in bold. They're the ones that are most commonly disproportionation reactions. Now, we can easily predict the most common oxidation state for each of these. And looking up, we can determine some of the other oxidation states for some of these as well. And for example, we usually think of chlorine. The most common oxidation state for chlorine is -1. Although, as you can see here, it is +1 as well. So this is one type of reaction where you have a simultaneous oxidation and reduction reaction. So if you have this reaction and you want to split it up into its half reactions, again, using the charges, the first thing we have is oxidation. So the one that goes through oxidation is the chlorine becoming the ClO minus. The reduction one is the chlorine, obviously, becoming the chloride ion. Now this one's kind of weird because if you wanted to say which one was the reducing agent, what would it be? Chlorine gas. Which one would be the oxidizing agent? Chlorine gas. So, just be aware. Yeah, you're like, oh, that's really... Yeah, I'm not going to ask that question right now, but that is, again, something we could do once we know oxidation reduction. Okay? So, that would be a slightly tricky one because you can go, again, both ways, and you have to be aware of that. If you see something splitting up into two different things, there's a good chance that this is happening. Now, when you look at redox reactions, the way we balance a redox reaction is we use what's called the half reaction method. This method is fundamental for all redox reactions. And the very first step is to write a skeleton ionic reaction. And usually this information is given to you. So once you have the skeleton ionic reaction, you want to split it into oxidation and reduction half reactions. The third step is to balance each half reaction. And in order, we're going to go through this process of first you balance all but the H and O, then you balance the O by adding waters, then you balance the H by adding hydrogen ions, then you balance the charge out by adding electrons, and then the very final step is only if it's a base, you add OHs, hydroxides, for each hydrogen ion if the reaction is in a base. So this is a rough outline of what we're going to do step by step for balancing redox reactions. So we're going to try to distill this into a process that we can use as a reference to help us balance any redox reaction, whether it's in an acid, whether it's in a base, whether it has HO or different elements in it. Okay. So if you do not have every single one of these steps written down, we're going to go through them step by step in detail. If you're like, okay, I got the gist. Skeleton, split, balance. There we go. So let's first look at the very first step. Skeleton, split, and balance is what we're looking at, SSB. And if you want to draw a picture there, you can, of a skeleton getting cut in half. So the worst show on TV, what is it called? Castle? Oh. This guy was a superhero and he cut somebody in half. So weird. He was like, had a whole outfit on. Bad TV. All right. So let's look at this. Skeleton. Okay. Dead body, split, cut in half, and then balance. Okay. You got to have the same amount on each side. So let's look at this. First is to write and identify the half reactions. So this is part of the skeleton. So we've got the given information. Iron 2 chloride and potassium dichromate solutions are mixed. Write the balanced reaction is what it asks us to do. Information here was given to you, so I apologize. Why it is that way would be a whole other thing to look at. We can look at that later as we look at this. So this is given to you, yeah. How to know that this is happening is a little harder. You would have to have either a reaction or a change that could show you that it was being oxidized and reduced. So, So this information here is then what we want to write the balanced half reactions for. We want to write the balanced reaction for the entire thing, but we first have to break it up into half reactions. So step number 1 is breaking it up into half reactions from this information here given to us. So to do this, we have to determine the charge on each of them, and the oxidation number based on their charges. So we've got iron with 2, chromium with +6, iron here +3, and chromium +3 here. So the first step is to identify what is being oxidized and what is being reduced, just like we did yesterday. So which is the one that's being oxidized, the iron or the chromium? Iron is losing electrons, and the chromium is gaining electrons. So that's step number 1, writing the half reactions. Okay? So once you have the half reactions written, step number 2. What's up? Yeah, this is the compound that is being reduced. Cr2O7 to Cr3+. You have to include the entire species. So it's this going to that, and that going to this. You can't just eliminate no because you feel like it. Yeah? What is being reduced? Yes.
But the reduction reaction is the one with...
Correct. Exactly. Yes. It's with dichromium. Mm-hmm. Absolutely. So, the next step is to balance all elements except for O and H. So, balancing all the elements except for O and H. So if you look here on this side, you've got 2 chromiums on this side and 1 on this side. So we have to put a what in front of Cr3+? 2 in front here. Now chromium's balanced, iron is balanced, oxygen, again, we're not doing that yet. So that's step 2. Step 3, balance all O's by adding H2O. So we've got O's, no O's in this one. We've got O's in this one. How many O's on this side? 7. So how many H2O's do we have to add to the right side? 7 waters. 7 waters. There we go. That's it. Step 3. Yep, H2O is what you add when you're trying to balance the O's. That's rule number 3. Step 3. So we've written the half reactions, balanced all but O and H, and then we balance the O's by adding water. Step number 4, balance the H's by adding H pluses. Now there's no H's, but you just added some H's. You're like, oh man, we didn't have any H's, now we do. Why did I do that? But you got to follow this rule. So you've got how many H's on this side? 14. So 14 H pluses on the other side. All right, that's step 4. All right, let's move on to step number 5 in order. Now, what could we be doing next? We got half reactions, we balanced. Balance, balance, balance. We got all the things balanced. What else do we need to balance now? And the charges. So let's see if that's our next step. Balance the total charge by adding electrons. So, in the first one here, we've got +3 and +2. Where does the electron go in this one? On the 3+ side, because it's negative. So we balance the electrons for that one. And now the bottom one. Got to do some math. We got how many positives here? 14 positives. How many negatives? 2. 14 plus negative 2 is what?
12.
Positive 12. So we got positive 12 on the left and positive 3 on the right. Oh, positive 6. Thank you. There's a 2 in front. Thank you for the coefficient analysis. Can't forget about those coefficients. So on this side we've got 12 positive. On this side we've got 6 positive, please. Thank you. So now we need to have where the electrons go. Right side or left side? Left side. And how many do we have? Of course, 6. That's it. Now, one cool thing you'll notice in the top one, where are the electrons? Right or left? Right side, right-hand side. Which side are they on the bottom one? Left-hand side. So you'll see the electrons must be on opposite sides of the half reactions. Ah, interesting. Now, is this oxidation or reduction with the ion? Oxidation. So in oxidation, some people like left and right side. In oxidation, the electrons are on the left-hand side. In reduction, they're on the right-hand side. Because reduction is a gain of electrons, oxidation is a loss of electrons. So,
Yeah, so it's reduction.
Yeah, so shouldn't it be reduction?
oh, I'm sorry, right side. Yep, you're right. Pardon me. All right, so oxidation is on the right side. Very good. It's on the product side. And then the electrons are on the reactant side for reduction. Again, they have to be on opposite sides. So if they're not on opposite sides, then you'll want to go back to step number 1 or 2 or 3 or so on. So we're on step number 5. What do you notice about these electrons, though? They are not balanced. So we want to have how many electrons on the right side if we have 6 on the left? 6. So all we have to do is take this equation here and multiply it by 6. So that is step 6 in this case. Equalize electrons. So equalize the electrons by multiplying the coefficients. So you multiply the whole equation by 6, the top one, and now the electrons are equalized. Some people would even call this just balanced, but equalized is another step, so you don't mix up these two steps here. Now the last step, I'm sorry, not the last step, step number 7, is to add the half reactions. So you're going to add the two reactions together and cancel out electrons and species appearing in both reactants and products. Species are either a ion or a compound or a molecule, and then electrons are the electrons in there. So we add them up. We just add up everything that's on this side and write it down, and then everything on the product side and write it down. So here's what's on the reactant side. 6 Fe plus 6 electrons, this and this, 14 H's, Cr2O7. And then on the product side, 6 Fe, 6 electrons, the chromiums and the waters. So it's going to be a long equation before we cancel anything out. Yes, sir?
Oh, wait, that's number.
We haven't canceled anything out yet. Okay, but just like in math, anything that's on the left side and the right side will cancel out if it's the exact same thing. So in this case, what things will cancel out? Electrons cancel. There's 6 here and 6 here, so they cancel. There we go. Oh, sorry. Let me go back. Takes a long time to write that down, I know. A lot of people are tempted not to do this step because it takes a long time just to write it down. And if you don't do this step, it's like, okay, why did I do steps 1 through 6? Because then if you mess up on step 7, it's like, it stinks. It's just takes a little bit of time. Just step by step. You take one step at a time. Each step is easy.
Can you just cancel this step?
Can you cancel it out up here?
Yeah.
Yeah. So if you're a little lazy like me, you just go, oh my goodness, I see two things that are on the same side. The opposite side, same thing. So I just go like this. I go, okay, I'm lazy. Yeah, 6 electrons, get rid of those. And 6 electrons, okay, Fe. Ooh, wait, Fe. Oh, that looks the same. Are they the same? No, not the same, because plus 2, 2 plus and 3 plus. So watch out, because sometimes you get a little, well, I've gotten careless before. But you still want to write out the whole equation, because you have an additional step based on what type of solution it's in. So you're really close to the end now. This is step 7. Baby step number 8. Okay, first step is write the half reactions from the skeleton. Step 2, balance. Step 3, balance the O's. Balance the H's. Balance the electrons. Get the same number of electrons and then add the half reactions together. Step number 8. If the reaction is in acidic or an acidified solution. So if you have an acidic solution, here is our equation and it's done. Don't have to do a thing to it. Yes? How do you know?
Yeah.
If you are told that it is in an acid, you're done. You will be told whether it's in an acid or in a base, or you will be told more information that will tell you it's an acid or a base solution. It'll either tell you or you'll have to know based on other information. Yeah, good question. Now, how do you know? Now, the other way you can know if it's an acidic or if it's in a basic solution, again, how could we test whether something was in an acid or base? How would we know if something was acidic or basic? The amount of H's, right. How do we test the amount of H's? You can count them. Good work. Good work. All right. So that's the cool thing. If it's an acidic solution, no problem. Now, the problem comes about when it's not an acidic solution. Okay, you look at this, you go, wait a minute, I got 14 H's. So it looks like it should be acidic. But if it is in a basic solution, it does not work this way. So, total charge must be balanced on each side. And for you to be completely done with this on step 8. If the reaction is in a base, an alkaline solution, for every H plus you have to add OH to both sides of the equation. Both sides. So step number 9, if and only if it's in a base. You have to add OHs. You're given that information, or you had to test for it by using an indicator or something else, or you had a previous information that tells you it's in a basic solution. But yes, given to you is the most common way of looking at these initially. So in this one here, it's a basic solution, let's say. So we would have to add an OH to both sides of the equation. So how many H pluses do we have on the left? 14. So we add 14 OHs to the left and the right. By the meaning of both? Now, we added the same thing to both sides of the equation. The reason why is in a basic solution there's lots of extra hydroxides floating around. So what ends up happening is these hydroxides that are floating around, they attach to the hydrogens, making water.
Oh.
So for every H in OH, water is formed, so it cancels out the OH minus and the H plus. So step 9b is to cancel out any waters that are formed. So you cancel out the waters formed by the OH and the H plus being added together in a basic solution. Because the OH concentration is so high, it neutralizes any H's that are floating around. So those cancel out, giving us 14 waters on the left side. There you go. And then you cancel out the waters, leaving us only 7 waters on the left-hand side. And 0 waters on the right. So in basic solution and acidic solution, you have a different balanced reaction. So in basic solution, that's when you will use the OHs and then cancel out any waters that form due to your adding of the OHs. So your final answer would look like this. With your 6 moles of iron 2 plus 7 moles of water, yielding 1 mole of dichromate, producing 6 moles of the iron 3, and 2 moles of the chromium 3, and 14 hydroxide ions in a basic solution. All right. So if we look here, steps we would go through for this problem, if you have iron 2 chloride and potassium dichromate mixed in acid, we follow the following steps. We look at, first of all, okay, writing the half reactions. Okay, then what do we do once we have the half reactions? Okay, all right, balance all but the O and H. What's step 3? Balance the O's by adding water. Oh, come on. And then you balance the H's by doing what? And the H pluses. Then step 5, balance the electrons. Make sure they're equal, of course. And we add them together. And there we canceled them out, added them together in an acidic solution. We are done as long as the charge is equal. That's it. Okay. So I would like you to now try to balance.
Oxidation and reduction.
We need our half reactions. Very good. So first thing you do is set up your MnO4 minus and your MnO2. So let me have your attention up here. Some of you are further along. Attention up here as you're working this out. Step by step, you'll want to walk through this. We'll have plenty of practice like this. First one is, you've got your I going to I2. In order for this to happen, is it losing or gaining electrons? Losing electrons. So that means this one is going to be what? Oxidation. This one's going to be what? Reduction. Okay? So once you have those equations, you balance all the elements except hydrogen and oxygen. So two I's, the MNs are balanced. You're good to go. Now we're on step 3. Balance the oxygens. What do we add to balance the oxygens? Water. So how many waters do we need to the right side? 2 waters. So now we go on to the hydrogens. Hydrogens. We've got how many hydrogens here? 4 hydrogens. So we need to add how many hydrogen ions? 4 to the left. We're on step 5 now. We've gotten through our balancing, and now we're on to our balancing of electrons. So, for balancing of electrons, you've got 2 here, 2 negative charge on this side. So how many electrons do you need on the right side? 2 negative. Yes?
So you don't need to balance the oxygens on the right, you only need to balance the oxygens on the left. So you just add water to the
Correct. When you added the water, you have 4 oxygens on this side. You added the water to get 4 on this side. So now the oxygens are balanced. The hydrogens are also balanced. Yeah? Yes? Please be quiet right now. I know you're trying to figure this out. We have a question?
supposed to find a difference between those 2 bottom ones and then
We're just balancing the electrons. So we just worked with the elements first. Now we got to balance the electrons. Then we can equalize them and add them up. So we got to go through, we're on step number 5 here. So 2 electrons on the right side. We look at the bottom one, we have a positive 4. Minus 1 is positive 3. On the right side we've got 0. So if you've got positive 3 on this side, we have to have negative 3 on that side as well. 3 electrons. So 3 negative plus positive 3 equals 0 net charge on this one. Now we have to equilibrate out the electrons. They are not equal, so what do we have to multiply the first equation by to get the same number of electrons? 3. So multiply this one by 3, that one by 2. So the top one by 3, the bottom one by 2. So with our multiplication and canceling out the electrons cancel because 2 times 3 is 6. 2 times 3 is 6. We got 2 iodides. 2 times 3 is 6 iodides. 4 times 2 is 8 hydrogens. 2 of these. 2 of those. 2 times 2, 4 waters. 3 iodines. That is our half reaction, but it's only in an acidic solution. So we're not done yet. What do we have to do now to make it basic solution? Add OHs. How many OHs? 8 to both sides. So we add 8 to both sides. The 8 OHs and 8 H's cancel out. We're left with 8 OHs on this side. Okay, there's, 8 and 8 give us 8 waters. We have 4 waters on this side, so they cancel out. 4 of these. And that's why we're left with 4 waters at the end. 2 MnO4s, 6 I's, 2 MnO2s, 3 I2s, and 8 OHs. So if you got close to this point, you may have just had the last couple steps to do. That's okay. That means you were on the right track. Okay. So 9 steps if you have a base. 8 steps if you have actually less than 8 steps. 7 steps if you have an acid. Yes?
How do you know how to put the electrons on the second one or the one? What are you looking at? Did you look at the negative?
So electrons on the second one. So look at this. I have a positive 4 on the hydrogens and negative 1 on the MnO4. So positive 4 minus 1 is going to be positive 3. cancel out the positive 3, I need to have a negative 3 because there's no charge on this side at all. Nothing's charged. So I can think of this as 0, this here as positive 3. I need to have negative 3 electrons to cancel that out. Now, one typo. For one of the problems on number 64D in your book, it's supposed to be going to Na+. So if you try to solve it without that typo, it will seem impossible because it is. Okay? On Friday, we are going to be doing lab number 4 on Friday. I'm going to move it back to Friday. We're going to be working on some of the skills so we can do what we're doing right now in the lab. So I'm giving you guys an extra day to process these half reactions and balancing them. You'll be using those in the lab on Friday. Okay. Your ion quiz, we're going to move that to Monday so it doesn't conflict with our lab. So this will be on Monday. And let me just tell you one thing we are going to be doing.
So what are we doing tomorrow?
Tomorrow we are going to start up on. Tomorrow we're going to be doing AP reaction prediction. We'll be starting on that with the reaction note handouts. So we're going through the AP reaction prediction and how to predict chemical reactions.